Thank you. It's great to be here. It's great to be at the BHI and back at Harvard. My talk is titled Black Hole Dynamics at Large D, and is based on a lot of papers. Okay. Fine. So what am I going to do? In this talk, I'm going to try to study the dynamics of black holes governed by Einstein's equation in a vacuum. Okay? I will sometimes generalize to Einstein's equations with a cosmological constant here. Okay? Much of the talk will just be about the vacuum. Now, so we don't have any complicated matter, no accretion disks, nothing fancy like that. These equations are very, very well posed, and yet they're pretty hard to solve. It seems unreasonable. It doesn't seem likely that we'll be able to solve the system analytically once and for all. And these equations, as you can see by looking at them, have no free parameters in them. Now, that's sort of bad news for an attempt for a theorist to reliably approximate solutions to these equations, because a standard tactic of a theorist to approximate solutions for a system you cannot solve exactly is to go to special values of parameters where the system simplifies, solve it at those special values of parameters, and then do perturbation theory. But if your system has no parameters, this is hard to do. Okay, so the idea of this talk is to sort of enlarge the problem and thereby endow Einstein's equations in vacuum with a parameter. This is I'm using a tactic that has been used several times before in physics. What we will do is move away from 4 dimensions. We'll study these equations, but in d dimensions. And we'll see that the equations, in some sense, simplify in the limit that d is very large. And our effective parameter will be 1 over d. Okay, so let's start. So, look. So what I've done here is to write down the metric of a black hole in d-dimensional space. Okay, so Schwarzschild black hole in d-dimensional space. Now, this may not look like a Schwarzschild black hole to you, and that's because I've perversely used a very strange set of coordinates. I've not written Schwarzschild coordinates, I've written what are called Kerr-Schild coordinates, because that will prove useful for me later on. Okay, doesn't matter very much. This is a black hole solution. By coordinate change, you can go from the form you're familiar with to this form. The important thing the point I want to make on this slide is that this metric here is flat space in these coordinates, flat space plus something. Now, that something is characterized by R0, the Schwarzschild radius of the black hole. And notice that if R is any value larger than R0, let's say 1.1 times R0, and you take d to infinity, then R by R0 goes to 0 very fast. Therefore, this term just drops out. Okay? So what we see is that so the space-time reduces to flat space. So what we see is that in large D, if you stay any fixed fractional radius away from the event horizon and take d to infinity, the space-time in that region is just flat space. Of course, once you're inside the event horizon, you realize you're not in flat space, so this argument breaks down somewhere. Where does it break down? Well, it's very simple to check that if you take R is equal to R0 and 1 plus something divided by d, and plug that into that metric, then that metric is no longer flat space. Then it goes to eta plus e to the power minus r. What that tells you is that in order to see that you've got a black hole rather than flat space, you have to come to a distance 1 over d within the event horizon. Okay? Because this is 1 over d within the event horizon. Okay. Great. So what's the conclusion? The conclusion is that black holes in large number of dimensions become very thin. The event horizons become almost like a little, the regions where it's not flat space outside the event horizon becomes like a little membrane of thickness 1 by d. Now what I'm going to do is the following. I'm going to take a metric of the same form that I wrote before, except that in order to get the Schwarzschild metric previously, we had this metric where u was any constant velocity, let's say 1, 0, 0, 0, 0, for the Schwarzschild metric at rest. And this function, this function r here was what we think of as r in flat space, namely just a radial distance and a spatial slice. That's what's written in fancy language here. In this metric here, I choose u I write the same form of the metric, but I choose U to be any smoothly varying one-form field in flat space. And I choose this function rho, which previously was which previously was R divided by R naught. I choose that here to be any smoothly varying function in flat space. Smoothly varying means, from my purposes, a function that does not vary on length scale 1 over d. You know, it has no, varies on finite length scale in the limit d goes to infinity. Okay. Now, I define n here to be the normal to surfaces of constant rho in flat space. And this function u here is any one-form field, but it's a velocity field, so it squares to -1. I also demand that u dot n is equal to 0, so that this velocity field lies tangent to the surfaces of constant rho. Okay. Now, as I've mentioned previously, I mean, the same logic for, I told you here that if r was greater than r naught and d was taken to infinity, we just got flat space. The same algebra tells us that if rho is greater than 1 and d is taken to infinity, we just get flat space. So what I've got is a metric which, whatever else it is basically flat space outside a certain region eaten out of flat space. Okay. Moreover, there's something special about the surface rho equals 1. One way of saying that the surface is special is to do the following calculation. Remember that this normal vector field, the normal to surfaces of constant rho, was, I chose it to be normalized such that n dot n was equal to 1 in flat space. Now what I'm going to do is to compute what n dot n is, not in flat space where this dot product is taken not in flat space, but in this metric itself. That's an easy calculation to do, and you find that n dot n is 1 minus 1 by rho to the power d minus 3. The interesting thing about this result is that when rho is equal to 1, n dot n is 0. What that tells us is that in this metric, the surface rho equals 1 is a null surface. Okay? We're going to argue self-consistently that this null surface will turn out, by the end of my talk, to be a very special null surface, will turn out to be the event horizon of this metric and its corrections. Okay? I'm going to assume that as we go along, and then we'll come back to seeing its self-consistency. Okay, so what have I done so far? So far, all I've done is written down a metric. It's a metric with a hole eaten out of space-time. Flat space outside that hole. It's a metric which has a special, which has an event horizon, as we will see later on. Now, I've also shown you that this metric is very accurately flat space outside a region of thickness 1 by d away from this event horizon surface. Okay. Now, what I want to do is to take this metric, which I've just written down, and turn it into a solution of Einstein's equations. Now, you see the region outside this 1 by d sort of fuzz of the solution is flat space, and that's an excellent solution of Einstein's equations. Now, there is the region inside the event horizon, which may or may not solve Einstein's equations, but for the purpose of this talk, I will not care. I only care about the solution as seen from the outside. Dragons could emerge inside the event horizon. I won't care. Okay, because it's causally disconnected from the outside. So I only need to solve Einstein's equations in a thickness of 1 by d around this surface rho equals 1. And then I've solved Einstein's equations. Okay, so what we do next is to take this ansatz and plug it into Einstein's equations. We note that in this ansatz, when we put these special values, the values that make this a Schwarzschild black hole, then Einstein's equations are just exactly satisfied. This is a special case of a more general algebraic statement that's easy to check, which is that if you choose these functions, this velocity field and functions to be any functions that obey del squared of 1 by rho to the power d minus 3 is equal to 0, del dot u is equal to 0, then Rm and Einstein's equations do not vanish, but are smaller than you would naively think. Now I have to explain this to you. Remember that our solutions had varied on a length scale 1 by d. Einstein's equation, like the curvature Rmn, is a two-derivative object. So naively, if you plug in any old metric which has this length scale of variation, RMN will work out to order d squared. And that's what happens generically. However, if you choose these special conditions on these functions, del square of 1 by rho to the power d minus 3 is equal to 0, and del dot u is equal to 0, then instead of Rmn being equal to order d squared, it turns out to be of order d. This has an important consequence. The consequence of this observation is that this object, while not a solution to Einstein's equations, is a good starting point for a perturbative solution to Einstein's equations in an expansion in 1 by d. How do you see that? See, suppose I take this, my true metric and say that it's the starting metric, the one I wrote down behind, plus a small correction times 1 by d times a correction metric. Okay? And I plug that into Einstein's equations. Well, the contribution from G0 is order d, and the contribution from the small correction is epsilon times order d squared, because it was not special, it's two derivatives, we get order d squared. But because of the explicit factor of 1 by d here, we get an extra 1 by d. So both these guys contributed order d, and therefore can be tuned to cancel each other. And so you can now try to correct G0 by a small parameter, 1 by d times G1, in order to get a solution to Einstein's equations not at order d, but at order 1. And once you've done that, you can go to order 1 by d, and so on. So this is a systematic perturbative procedure. Okay? So it turns out to be possible to do this, okay? I don't have the time to tell you in any more detail. You can take Einstein's equations and divide them into the dynamical equations that look at evolution in the rho direction, and the constraint equations that constrain data at fixed rho. Turns out to be possible to just exactly solve Einstein's equations, the dynamical Einstein's equations. Once you put all the right fixed gauge, blah, 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 the solution is unique, given the data that we looked at. What remains is the constraint equations. Okay? Now, there's this lovely property of Einstein's equations that if you solve the dynamical equations everywhere in space, then all you need to do is to solve the constraint equations in one sliced space. Okay? It turns out to be convenient to choose that slice to be our event horizon slice. And when you do that, you find that the constraint equations are not automatically satisfied with the dynamical equations are satisfied, but they boil down to an interesting set of equations. They boil down to the equations that a stress tensor that lives on this membrane surface viewed as a submanifold of flat space, not of the true metric, is conserved. The stress tensor is entirely localized on the submanifold, that's this delta function here, and its components are entirely tangent to this manifold. Okay? And therefore, the stress tensor can equally well be thought of as a world volume stress tensor, one that lives not in space-time but on the world volume of the stress tensor. Now, Einstein's equations tell you what the form of the stress tensor is. I'm giving you the answer to leading order in 1 by d. We worked it out to one higher order. The Einstein's equations tell you what the form of the stress tensor is. It turns out to be the sum of two terms: a fluid stress tensor and something we're going to call the total derivative stress tensor, which is basically just the Brown-York stress tensor of this surface viewed as a submanifold of flat space. Now, it's something that's sort of easy to check and very important for the consistency of this whole program is that the conservation of the stress tensor normal to the direction of the membrane turns out not to be an equation but an identity. If you just plug the stress tensor of the previous slide, I haven't given you all, well, you plug the stress tensor in and you just compute the conservation of the stress tensor normal to the membrane. That works not as an equation but just as an identity. So the only non-trivial equations are the conservation of the stress tensor in the direction, in the tangent directions of the world volume. Now, for that, in order to evaluate those equations, we note the following. We note that the Brown-York stress tensor of just this surface viewed as a submanifold in flat space is automatically, identically conserved in the tangent directions. So the conservation gets contributions only from the fluid part of the stress tensor, and the fluid part of the stress tensor is very simple. It's given by a pressure term and a shear viscous term. The shear viscous term comes with coefficient 1. The pressure term comes with a coefficient that is a complicated function of the extrinsic curvature of the metric viewed as a submanifold of space-time. Okay, so our membrane equations are simply the equations of conservation of this fluid stress tensor. Fine. Okay, now there's an important counting problem we have to do. Because we've got conservation equations on the membrane world volume, we've got d-1 equations. If you think about what the variables of my problem were, you see, there's something that I should have said. When I started out my construction, I started out with a velocity field and a shape of the membrane. Okay? How many variables were there in that? The membrane shape had one variable because it's one function. The velocity field had d-2 variables because it's one velocity field on a d-1 dimensional surface, and there's the identity u squared is equal to -1. So total number of membrane variables was d-1, d-2 plus 1. The total number of equations is d-1. So we have as many equations as variables. And therefore, plausibly, a good initial value problem entirely in terms of the membrane. Okay? I've made a comment here which I don't have the time for, which says that this sounds a little bit like the membrane paradigm from the 1970s, except this thing I think is useful. Okay. 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 Our membrane comes, just as a matter of algebra, using the membrane equations, you can do the following. You can show that the conservation equation of the stress tensor dotted in the u direction gives you del dot u is equal to sigma squared by something that is, at least in the large D expansion, positive definite. Now, this equation has an interpretation. If you pull back the Hawking area form onto the membrane, you find that that gives you an entropy current which is u mu by 4. And this equation just tells you that our membrane hydrodynamics comes equipped with an entropy current that is always positive. Entropy is always locally produced. This is just the membrane dual of the Hawking area increase theorem. Okay. Now, as this membrane moves around, it radiates. It's sort of interesting. It's easy to compute to leading order in the 1/d expansion what the radiation is. And the final result, I won't go through this, won't surprise you. The final result is that the radiation that you get is exactly the radiation you would have got, the linearized radiation you would have got from a probe source carrying stress tensor T mu nu, the T mu nu that I've given you on the membrane, sourced by that T mu nu. What's sort of interesting is that there's a kinematic factor of feature in large D, which ensures that though the stress tensor is not small, the effective radiation is very small. It's a fact about large D Green's functions, which I don't have the time to explain to you, but it tells you that the radiations of order 1/d to the power D. This, so it's minuscule. This is totally crucial to the consistency of my story. You see, that's why the membrane could have autonomous local equation dynamics by itself, because radiation here is not non-locally communicating with the radiation there. There's a sense in which the large D limit is a decoupling, a Maldacena type decoupling limit for Schwarzschild black holes. And radiation is the failure of that decoupling, occurs at order 1/d to the power D. Okay, so we've repeated this construction in many contexts, not just in flat space, around any smooth solution to Einstein's equations with a cosmological constant, with charge, for Einstein-Maxwell theory, and so on. Okay, and I very quickly want to tell you about equilibrium solutions in this theory. So now consider a solution to Einstein's equations, perhaps with a cosmological constant, which has a killing vector, a time-like killing vector k mu. Okay, I'm going to search for all stationary solutions of my membrane equations. Turns out that you can very easily show that all stationary solutions have to have u mu proportional to a time-like killing vector. Okay, that's a theorem you can prove from these membrane equations. Turns out that the remaining membrane equations simply boil down to the following statement, that this k tilde quantity, the complicated quantity that came behind the pressure in our membrane stress tensor, is proportional to constant, which will soon be interpreted as the temperature of the membrane, divided by this, the norm of the killing vector. Okay, so stationary solutions are very simple to find in this membrane picture. U mu is just given by the killing vector, and the extrinsic curvature with some corrections is given by a constant. Okay, once you have these once you've got these, the membrane equations are dissipative. So you might have asked, can you write down an action for the membrane? Of course, the answer is no, because it's dissipative. I mean, you could maybe in fancy terms, with double formalism and so on, but simply no. However, when you've got equilibrium, there's no dissipation. So you might ask, can equilibrium be generated by an action? 2 minutes, please. Okay, so can equilibrium be generated from an action? The answer is yes. You can find an action whose variation produces this equation of motion. And the action is very simple. It's just an integral of the Gibbons-Hawking term plus an integral of, well, something like an area term normalized by the Killing vector, plus when there's a non-zero cosmological constant, the integral of a volume term, the volume contained inside the membrane. Easy to show that the variation of this action produces the stationary membrane equations, and also that the variation of this action with respect to the metric produces the correct membrane stress tensor. Also easy to show that this action, when you evaluate it on shell, reduces to the free energy of these membrane surfaces, of these stationary solutions. There's a pretty story here that I don't have the time to explain to you. One more thing to tell you is that, you see, it's easy that now with this formalism to find particular stationary solutions of the black hole. Simple stationary solutions include just like Schwarzschild black holes in, for instance, ADS space. Of course, the solution's trivial. The interesting thing about it is that our membrane equations reproduce the thermodynamics of these solutions exactly, to all orders in 1 by d, correctly in d equals 4, not just at large d. Not terribly sure why that had to happen, but it's sort of nice. Okay, this does not as yet work for rotating membranes, but that may be, we may be able to improve the membrane equations in order to make that work. Turns out that the fluid, it's easy to recover fluid gravity from this picture. Fluid, if you've got slowly varying membranes in ADS space, the membrane equations can be transformed to equations on the boundary, which reduce to the equations of hydrodynamics, order by order and derivative expansion. Turns out that like I said before, to zeroth and first order and derivatives, we get exactly the right hydrodynamical equations at finite d, not just at large d, using this picture. You see deviations at second order. Okay, I'm almost done. You can compute the spectrum of small fluctuations around, let's say, spherical membranes and look at their spectrum. Compare that with computations of quasi-normal modes around spherical black holes. You find a perfect match in the 1 over d expansion. Okay, that's it. So I've got a summary. You don't need it since you've all been listening so carefully. And what might this be good for? This is the last thing I'll say. Well, when I was writing this transparency last night, it occurred to me there are 3 talks from yesterday, or maybe 4 talks from yesterday that might in the ultimately optimistic world have some overlap with what I'm saying. Firstly, you might be able to use what I've said as an approximation scheme for what happens in d equals 4. Now, we had a talk yesterday in which part of the evolution of mergers was described by quasi-normal mode dynamics. Something I didn't have the time to say is that my membrane equations were effectively a nonlinear theory of the lightest quasi-normal modes. In the talk yesterday, the last part of the evolution was described by just linearized quasi-normal modes. Perhaps you can do better by using these membrane equations because they correctly capture a set of nonlinear effects. Okay, that's it. Just okay. Okay. Then there might be a connection with Aaron Wall's talk from yesterday. You see, when you've got a reformulation of equations, it might be useful for practical purposes. I think in this case, it's much more useful to be likely for structural questions. One structural question you could try to ask is, suppose we repeat all this for higher derivative gravity rather than Einstein gravity. What kind of membrane equations do we get? Do we always get equations with a positive divergence entropy current or not? If so, can we compute that entropy current and relate it to walled current, at least at large d? If not, can we restrict allowed equations of motion of high derivative gravity, classify those into those that have good thermodynamics and those that don't? Finally, Malcolm Perry yesterday suggested that there was an interesting conformal field theory on the event horizon of black holes. If what he said could be generalized to arbitrary d, perhaps we could see evidence of these anomalies in the hydrodynamics. Something like this worked out in the fluid gravity correspondence, for those of you who followed that story. Okay, this is just random comments, but there's a lot to explore. Thank you. Sorry for going over there.
So have you thought about the actual merger of black holes, where your membranes might combine?
Yeah, I've thought about it a bit and not yet managed to make quantitative progress there. I think it's plausible that in large D, we could actually find that merging solution. We've not yet managed.
And D?
I should add that our membrane approximations break down at that point. It's very much like when you have two soap bubbles. Hydrodynamics describes them when they're doing this, but they wouldn't describe this actual singular thing. You need atomic physics for that. So we have the analog of atomic physics. We have all of Einstein's equations. We just have to be clever now.
Have you thought about, is there anything simple that could be said about a microscopic theory of the membrane at large D? Or this matrix structure is kind of suggestive.
Yes, yes, that my remark about Malcolm's, Malcolm's talk was going in that direction. If there is such a thing, if quantum gravity, a Lorentz invariant quantum gravity in a arbitrarily large number of dimensions, if there is an example, turns out to be a consistent example of such a theory, then your question is, of course, very pressing. And if this turns out to be the case, then my membrane dynamics would be to that microscopic theory as Navier-Stokes equations is to n equals 4 Yang-Mills. Right. So what you would want to do is to get some information about that microscopic theory from what you see about the hydrodynamics. Typically, what's easiest to see is things like anomalies. So I was wondering whether, well, if the story could be rerun in arbitrary D, maybe we could somehow pull out the anomaly from my hydrodynamics.
So Shiraz, your metric is, you've restricted yourself to a spherical topology, right?
No.
I thought your coordinate system that you're using is spherical, is it not?
No, I'm sorry. I'm sorry to have been so unclear. There are two places where I wrote down the metric. This one was as an example to motivate the construction.
Okay.
On the next slide, U mu here was any one form field in space-time. Spherical, non-spherical, anything. Rho was any function. So what we can describe is the most general motion of black holes in flat space. No spherical, nothing.
It can be torus, for instance.
It could be anything. In fact, there are interesting solutions to the stationary equations. It's very much like soap bubbles. And there are interesting solutions to these equations that have all kinds of topologies.
Yeah. I'll be very brief.
Yeah. So if there are extra dimensions, and I guess it depends on the compactification scale as to whether there are observable consequences to that, or have you thought about that?
Yes. So, there are two possible uses for this. Of course, it would be great if the real world had 1 zillion extra dimensions and we could use the stuff there, but that's not very likely. The way I'm looking at this is as a theoretical tool to explore structures of Einstein's equations by introducing a new parameter, even if that parameter does not actually exist in the real world. I doubt that what we're doing will be relevant to extra dimensions of the real world. That's it.
Thank you, Shiraz.